Hello everyone. Previously we have seen force vibration systems and how can we solve those questions. Also I have clearly mentioned all of the steps step by step to how to solve a question using modal coordinates and get back the response in the original coordinate. Now we'll tackle the system which are having dampers in them. So now force vibration of viscously damped systems. So generally the systems which are not not force, they are also not damped, and the systems which are having dampers, they are generally force or they are getting external forces. That's the thing. So our aim is for modal reduction, that is using this modal. So one of the application of modal coordinate system is we can reduce data size without losing the actual data. So that's what we have shown earlier also. We have reduced the response. So we had a response size of this much, and when we change the response to modal coordinates, the response size has decreased. And how can we decrease this? We have just used this extra matrix, M and X, or change of basis matrix, which is just a combination of eigenvectors. But storing a value of X or change of basis matrices or eigenvectors, I can store a huge amount of data of Q or modal coordinates in the original coordinates in Q, which are modal coordinates. So I'm going to convert a huge amount of data into smaller amount of data, and I have to alongside store some extra values of eigenvectors, but and that's all. So that's the part which is attracting us. And now in the damping system also, we'll try to use the same concept of what we have seen earlier of eigenvalue problems to solve our equations, which are not directly applicable. So we want to do something to apply the eigenvalue problem. So this is the general equation of motion which will be there: mass matrix into acceleration vector plus damping matrix C into x, that is the velocity vector, plus x dot, that is velocity, plus stiffness into displacement is equal to the forcing function vector. And x, when we see down, this x are eigenvector matrices of this. So how have we got this? We substitute the normal mode condition, that will be small x is equal to the amplitude into cos omega t plus phi. That is the normal mode condition where the system is oscillating in some frequency omega itself. So all the mass are oscillating in the same frequency, and after substituting that, we get such equation which has reduced formats. And then we are converting it to modal coordinates also directly. So we have used that change of basis matrix, and now we have pre-multiplied it with x transpose, that is change of basis matrix transpose. So the transpose must be outside, not inside. This transpose must be outside. Sir is also so. And now we know that this combines to an identity matrix if this x, the modal eigenvalue vectors, are modal vectors or mass normalized eigenvalue vectors. So we can do that, and we can get identity which is called as modal mass matrix. And the main point is this is a diagonal matrix. Now let's come to this x transpose kx. That is also omega or lambda or eigenvalue matrices. So we have all the eigenvalues, omega 1 square, omega 2 square, omega n square. So this is called as modal stiffness matrix, which is the stiffness matrix of the modal coordinate system. But the main part is this is also a diagonal matrix. So of off diagonal elements are zero, or the entries are zero. Here also identity matrix means we have zeros over here. And let's come to here. So this is the forcing function or force vector, which is converted to a new coordinate system. So this is the point of study, which is the new part for us. So let's come to that part. So this by default will not be a diagonal matrix, because x was the eigenvector matrix of the generalized system, which was this k minus m omega square into x is equal to 0. And x was independent of c values. This x was independent of c values, the eigenvectors which we have got. So we can get this combination x transpose cx as diagonal matrix by assuming it to be a special type of damping matrix. which is called as Rayleigh damping. So in general, this matrix will not be a diagonal matrix. We want it to be diagonal matrix. Why? Because if we have a diagonal, it as a diagonal matrix, we can combine this. We can substitute Q is equal to Q cos omega t, that is normal mode condition. Combine all the coefficients of Q and invert this and directly get the eigenvectors. Or the second part is we can, since we have converted it to modal coordinate system, we want to decouple the system, and that is only possible if we have only the diagonal entries in all the coefficients, and if non-diagonal entries are non-zero, that is these are non-zero for this matrix, then it will be tough, or it is not possible. It is not called as decoupled system. We want to decouple the system. That's why we want only diagonal entries. So if we assume a new type of damping model, which is Rayleigh damping model, or the damping is kind of a Rayleigh damping, then we have diagonal matrices for this matrix also, this multiplication of matrices. And in that case, we can apply eigenvalue problem, the solution to it, and get the values of the response. So we'll end over here. In the next video, we'll start at the details of Rayleigh damping.